Welcome to this lecture series in group theory. Today we'll be looking at an example of, or rather two examples of groups. These are very fundamental examples. So let's recall what we did the last time. Last time we defined what is a group. So a group was defined as a pair where G was just any set and star was a binary operation, which means what? Which means star is a function. Binary operation on G just means that star is a function from G cross G to G. Yeah, so a group is a pair, G and star, where star is a binary operation on G, such that three properties are satisfied. The first is associativity, meaning A star B star C equals A star B star C. And now, of course, we need to understand what does this mean. Star is a function from G cross G to G. So what does this mean? This is a natural way to express. This is nothing but star of B comma C. So instead of writing this thing, which is kind of unnatural for us because of our upbringing, we write addition as 2 plus 3 and not plus of 2 comma 3. If you're programming things, then maybe this kind of thing is useful. But anyway, what I'm trying to say is that this is just a change of notation from that to this. All right. So this is associativity. This should happen for all A, B, and C and G. The second is that there must exist an identity element, which means that there is some E such that E star X is X star E equals X for all X in the set G. And each element has an inverse, meaning for all things in G, there exists something X prime such that X star X prime equals X prime star X equals E. So before we even make this statement, we showed that this guy is actually unique, even though we have only insisted on its existence. So there is a unique identity, and this thing is equal to that unique identity. Also, before we move on, we suppress star from our notation. So instead of writing A star B, we just write AB and have it understood that this actually means A star B. When there are multiple binary operations on a group, which I don't think will ever happen in our situations, then of course we cannot afford to suppress this notation because then it will cause confusion. So that's that. But in general, we will just write AB, things like this, and hope that it is understood that it means A star B. Also, this guy is called the inverse of X. In fact, this is also unique, so we showed that. If given an X, there is only one such X prime which can satisfy this. And we denote it by this symbol X to the power minus 1. So this is the notation for inverse. We introduce this another notation where we have some, let's say, a natural number. Then X to the n denotes this. If X were 0, then X to the 0 just simply means the identity element. And if X is raised to the power minus n for some positive integer n, then this is X inverse dot X inverse n times and so on. So we introduced that notation. And then lastly, we discussed that this equation, suppose you think of X as an unknown. So this equation is written in a group. A and B are elements of the group. Both of these equations have unique solutions. Think of X and Y and as unknowns. Both of these have unique solutions. In fact, you can explicitly write down the unique solution. It's nothing but this and nothing but that. Okay. And also there is this cancellation property that suppose this kind of thing holds, then you can just sort of cancel A out and write that. And what is happening really is that you're composing with, sorry, not composing, but you're multiplying with. Also, when I say multiply, I just mean operate by star. So generally we use the word multiplication, but there is no such thing as multiplication as such. It's only this operation that we can do on this pair. There is no other operation in sight. So basically you just A inverse star A star X equals A inverse star A star Y, and using associativity you'll get X equals Y. Similarly, there's this other counterpart. It's exactly the same kind of proof will show you that X equals Y. So this was basically what we did in the last lecture. We also made a comment that, motivational comment as to what is all this trying to capture. This is trying to capture symmetries. So a group is supposed to be the set of symmetries of some abstract object. The object is hidden from us. We kind of forget about the object, you could say. And if you have, three symmetries, then you apply the first two of them or the third one, or you kind of do it in this order. It doesn't matter. That's what associativity is trying to capture. Identity element is trying to say that if you don't do anything to the object, just keep it as such. That should also count as a symmetry. So that's that. And each element has an inverse. So if you apply a symmetry, you can undo it basically. So that facility should be there, and that's what a group is trying to capture. So it just take some basic properties from what we expect from the notion of symmetries. This is how we make the notion precise, you could say. There is no definition to the word symmetry as such. The notion of a group is making that precise. All right. These are the problems, and this is an important problem. Every problem is important, but this is important from the theoretical standpoint, because it says that suppose you just have sort of a one-sided inverse, then actually that's a two-sided inverse. So mull over this as to what this is trying to say, and proof is not hard. Anyway, so now let's get to the material of this lecture. We will define what is the symmetric group. So suppose X is a set, any set, doesn't have to be finite, just any set. Recall that a bijection from X to X, also written in this fashion, this is just a function. So a bijection from X to X, let's call it little f, is called a permutation of X. So we are just defining what we mean by a permutation. It's nothing more than a bijection. A bijection from X to X is called a permutation. So it's just we could have just used this word, but we will, when we are discussing group theory, this is the word that is used. It depends on context anyway. So this is a permutation of X, and we define the symmetric group. Okay, all right. So the set of all the permutations is denoted by the symbol, and this is called the group of symmetries. So before even we can use that phrase, we should just justify that this is a group, and before we can justify that this is a group, we need to make precise what do we mean by the binary operation on it. So we have to explicitly describe the binary operation. Okay, so we have defined a permutation, and we have just introduced a notation for the set of all permutations of X, meaning the set of all bijection as this or that. This is sim_x or Sx. So here is the thing. Another notation, if X is this set 1 up to n, then we write this instead of that, because that thing is quite cumbersome. So we simply write that. I might also use sim_n, but I don't think this notation is in usage in the standard literature. Alright, so now we'll describe the binary operation. What is the binary operation? Star is defined as f star g is just f composed with g. So recall, what do we mean by composition? So composition is a function from x to x which takes little x to f of g of x. So g of x is a member of x because g is a function from x to x, and we just operate f on it. So this is how composition is defined. Diagrammatically, one can represent it as such. So you have f, first you apply g and then you apply f. So this thing is f composed with g. So this is a very nice way to sort of pictorially represent what's written here algebraically. Okay, so that's what the binary operation is, and now of course we need to verify the three properties. So associativity is very simple because function composition is associative. So composition is associative. One can verify that. This, if you're not convinced, you can just verify this. Composition is associative. What do you need to verify? You need to verify that f composed with g composed with h is f composed with g composed with h whenever f, g, h are functions from x to x. They don't even have to be bijective functions. This is true even for non-bijective functions. It's even true in more generality, but we don't need to go in more generality. Okay, what about identity? Does there exist a function f such that f composed with g equals g composed with f equals g? Of course there is. The identity function. Which function? Let's say this denotes the function which doesn't do anything, it just takes x to x. So of course if you compose anything with that, you get that. So therefore the identity does exist. And lastly, inverse. So if f is in sim x, meaning f is a bijection, you can just define f inverse of x as y where, let me not write f inverse, let me write g of x is y where y in x is the unique element in x such that f of x equals y. I'm just taking inverse of a function. I'm already assuming that you're familiar with the notion of a function, inverse, bijection, injection, all of that. The set theoretic language you are familiar with is what I'm assuming, but anyway, let me spell a little bit out. So we have the set x, this is the same, another copy of x, and let's say this is y. Since f is a bijection, there is one and only one thing, little x, that maps to y under f. So all we are saying is that define g of y as the element of x which maps to y under f. And you can just verify that f of g is g of f is the identity. All of this is very, very trivial. So this is indeed a group. Sx equipped with star is indeed a group. And now from the philosophical standpoint, what is it capturing? It is supposed to capture the symmetries of some object. Well, it is capturing the symmetries of x. X is a set, there is no more structure to it. The only information a set has is its cardinality. So the only way to preserve the structure, so to say, there is more to be said there, but philosophically speaking, the only way to preserve the structure of a set is just bijection. A bijection preserves the cardinality, right? So this group of symmetry, all the bijection, all the cardinality preserving maps. Because cardinality is a property of a set, and the group of symmetries of a set is, or the symmetric group of a set is the cardinality preserving maps under composition. So that's what motivates this definition. All right, linear groups. So this time now we have a vector space over some field f, and if you're not comfortable with arbitrary fields, you can for now just think of real or complex vector fields. Sorry, real and complex fields, not vector fields. So we write GLV. We write GLV to denote the set of all invertible linear maps from V to V. So these are linear isomorphisms, basically. Okay, so this is a notation, and we define star as just the composition. So T star S is just T composed with S. If we have two invertible linear maps, then this is how we define the binary operation. And one can again verify that this is a group. So that I leave as an exercise, that this guy is indeed a group. And this is called the general linear group of the vector space V. What have I done? So it's what have I written? General linear group of the vector space V. Okay, so again, philosophically, what is it trying to capture? Now, V is a vector space, so you can also think of it as a set. So we could have just considered S, or we could have considered sim V. But sim V is forgetting all about the linear structure that we have in V. It's just considering V as a set and taking the cardinality preserving maps. But there is more structure in V, so we could ask for those bijections which preserve that structure. And of course, what structure? The vector space structure. So the linear maps are the maps which preserve vector space structure. So linear structure preserving maps are what constitute the general linear group of a vector space. Okay. Clearly, GLV is contained in SymV as a set. GLV is contained in SymV. Every member of GLV is, of course, a bijection in particular. So, because we are preserving more structure, more than just the cardinality, we get a smaller group, right? So, I hope you understand what's going on. And take it as an exercise to show that this is indeed a group. That's important. Okay. Last piece of notation before we finish this lecture. Instead of writing GLRN, we write GLNR. This is another notation that is frequently used in literature. So when you see this, we just mean the symmetries, linear symmetries of Rn, meaning all the invertible linear maps from Rn to Rn, where Rn is the vector space over Rn. It's under coordinate wise addition and multiplication. More generally, we write GL f to the n as just GL and f, where f is any field. Doesn't have to be real or complex field, any field. So yeah, this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.